All right, today is a big important day. It's not hard. Buffers alone, finding the pH of them is actually a lot easier than what you've already done. So today will be a nice light day. It's when we come back on Monday, when we put it all together, is when your head will spin a little bit. So it's important that we understand what buffers are and how to find the pH of buffer solutions. So what a buffer is, what its true definition is, it is a weak acid and its conjugate base, or a weak base and its conjugate acid in combination with each other. What a buffer does is it helps resist pH change. So, for instance, in our body, in our blood, we have buffers that protect us from acid-base invasions from different things in the environment, or sometimes you get acidosis if you're sick because you're producing a certain amount of H+ and all this kind of stuff. So what a buffer does is protect the pH levels in our body, protecting all our organ systems. So for instance, we have carbonic acid and hydrogen carbonate in our blood. So how does that help maintain pH levels? Well, let's say for some reason something's undergoing acidosis, and somewhere in your body you're spitting out a lot of H+ into your bloodstream. If H+ is added, which component of the buffer will this react with? The HCO3-, correct. So we get H+ plus HCO3-, and we do that, we make H2CO3. So theoretically, we took a strong acid and we turned it into a weak acid. That helped maintain the pH level. So that protected us. What happens if somehow we get alkaline? Something happens where we're dumping OHs in, or some other sort of base. What is that going to react with? The H2CO3, and it will make what? HCO3- and water. So we took a strong base, and we protect our bodies by turning it into a weak base. So that's what a buffer does. A buffer helps maintain pH levels. Does that kind of make sense with the everyday definition of a buffer? What is a buffer in English? We say he's the buffer to our argument, or yeah, the go-between, the blocking, whatever. I don't even know what the real definition of buffer is in English. But anyway, it kind of makes sense. The buffer is keeping things as they are, keeping the acids away and keeping the bases away. So what's important for you to know is how to recognize a system as being a buffer. You need a weak acid in its conjugate or a weak base in its conjugate. And the conjugate, you're not going to find this guy in a bottle on a shelf. It's always in the form of a salt. So your conjugate will be like carbonic acid and sodium hydrogen carbonate. So the salt is going to contain the conjugate. So that's the most difficult part, is recognizing. Once you do, we're going to use a super sexy formula called the Henderson Hasselbalch equation. It seems to be a really popular thing. When my dad was hospitalized for a while, many years back, spent a lot of hours in the hospital. And so you make conversation with all the doctors. Oh, where are you from? What do you do? And they ask me all these things. And it's like, I teach AP chemistry. And the guy was like, okay, do you know Henderson Hasselbach? Like, that's the only thing he remembered. So, which makes sense. I think they use this a lot for pH levels in body systems and things. So yeah, I impressed him because I knew Henderson Hasselbach. It was kind of sad. Anyway, there's two versions of Henderson Hasselbalch. There's an acid version and a base version. The acid version is on your AP sheet, so you don't need to memorize it. pH is equal to the pKa plus the log, and you always put the ion, the conjugate, over the acid or base concentration. Ion over acid, ion over base. No matter what, the charged species goes on top. The POH version is not on the sheet, but you don't need it because you just replace pH with POH and Ka with Kb, and it's over base. So it's the same equation. POH is equal to the pKb plus the log of the ion over the concentration of the base. These have to, I'd say they have to be in concentration. We'll get to that Monday. For today, these have to be concentration. All right? So all you do is plug and chug once you recognize you have a buffer system. So the first one says, calculate the pH of a solution, which is 0.53 molar. That's nicotinic acid. And sodium nicotinate, 0.5 molar of that. I had to look it up. The Ka for nicotinic acid is 1.4 times 10 to the negative fifth. All right. So this is just adding now a level of recognition we need to do. Identify. What is this? Classify it. Weak acid. What is this? It's a salt, right? But what does that salt contain? Do you see how it's where are we getting strong from? No, the sodium's just hanging out. It's not doing anything. The sodium's actually just going to come off, leaving behind C6H4NO2 minus. What can you tell me about this in relation to that? Yeah, one of the H's from water will go over there, but we're not undergoing hydrolysis because we have a system here. We have a buffer system. Look at that thing. How does it differ from the acid? Okay. What can you tell me about conjugate acid-base pairs? They differ by an H+. Does that not differ by just an H+? So that is a weak acid, and it's what? Conjugate base. That is crucial. You have to pick up on that. This being a salt alone means nothing. You've got to look at the system as a whole thing. So we have a weak acid, and we have a salt that contains the conjugate base. That makes it a buffer. So now all we have to do is plug and chug into Henderson Hasselbalch. pH then is equal to, what does pKa mean? P is the old-fashioned way for what? Negative log of the Ka, which we figured I looked up to be 1.4 times 10 to the negative fifth, plus the log, the concentration of the ion on top of the concentration of the acid. So what goes on top? Correct. 0.5 divided by 0.53. All right, so let's go ahead and solve. And we need, yes, 2 decimal places, 4.83 for 2 sig figs. Now, one thing that with buffers, I don't want you to worry too much about it, but a lot of times I tell you, look at the answer. Does the answer make sense? It's a weak acid, so it'd be acidic kind of a thing. In buffers, you really can't predict whether or not, since this is a Ka, whether or not the pH is going to be acidic or basic, because it depends on what you have here. Yeah, this is an acid, but that's a conjugate base. So technically that could be super, super high concentration with a very low concentration of this, making this whole thing basic. So you can't depend on it matching up. Does that make sense? Okay, this is the only time you really can't, is in buffer systems. All right, let's do this next one. Calculate the pH of a solution that is 0.254 molar NH3 and 0.254 molar NH4NO3. What do we have? What is NH3? Weak base. This is a salt, but what does that salt contain? NH4 plus, which is what? The conjugate acid to that base. We have a weak base and it's conjugate. That means we have a buffer. But we know ammonia is a base. And when you look it up, the Kb is 1.8 times 10 to the negative fifth. So what version of Henderson Hasselbalch do I have to use? The basic version. POH is equal to negative log of 1.8 times 10 to the negative fifth plus the log. The ion's concentration, which is the NH4 pluses, is 0.245. And then this one is, 0.245. What's the log of 1? 0. Okay, so those cancel. what do we get? The POH is equal to, I want you to see something real quick. Do you see how that goes away? And that the POH is really then equal to the PKB? Does that look familiar? When did we do that? The half titration. And I'm going to show you in a rice table how these two are the identical things. Using Henderson Hasselbalch is just a logarithmic version of a K expression. And I'll show you that in a minute. But go ahead and solve POH. And is that what we're looking for? I need one more decimal place. 4.745. Okay, and then what's our pH? 9.255. So for those of you who took pre-AP, you actually learned this, but we call it the common ion effect. And you used a rice table. This is a lot faster than using a rice table, don't you agree? Okay, but let me just show you. If you were going to do this with a rice table, just want you to see the connection. So if we were going to do a rice table, we would always take the weak acid or base and add it to water. That's always the rule. And we'd make NH4 plus OH minus. We have a concentration of here of 0.245, 0.245, because that's what we have, and 0, minus X, and plus X. And so we get 0.245 minus X, trumps that, 0.245 plus X, trumps that, and X. So when we write our expression, our KB is equal to our NH4 plus times OH minus divided by the NH3. We know this is the same. Those two are the same, right? So what happens to them? They cancel out. So we'd get the KB equal to the OH minus, which is basically the KB is equal to the X, which is the exact same thing as taking the negative log of both sides and getting this. So this is just a faster way to do the same thing as doing a rice table. I really don't encourage a rice table on this. You can. If you want to do rice tables on buffer problems, you always take the weak acid or base and add it to water, and it will produce the conjugate. And you have initial concentrations then of both of those things to put into the I line. All right? But again, that's a lot more work solving than doing this. This took long right now because I've been talking a lot about it, but when you start rolling on them, they're really, really fast. Okay? All right. Let's go on and do a different one. It says, calculate the pH of a solution prepared by mixing 20 mils of 0.3 molar acetic acid with 20 mils of 0.350 molar sodium acetate. So let's identify our parts. Acetic acid, what is that? A weak acid. Sodium acetate. That's a salt that contains the acetate ion, which is the conjugate base, right here, negative. Okay, so we know we have a buffer system. Can I just do Henderson Hasselbalch and put 0.3 and 0.35 in there?
Yeah, because you have your chains there, so
Yes, I'm putting them together. They're diluting each other, so we need to do MV, MV. Here's a happy fact. If you want to use for acetic acid, HAC, I'll let you. And if you want to use AC minus for acetate, I'll let you, because they let you on the AP. So instead of having to write C2H3O2 over and over again, it's kind of nice. So acetic acid, if we do MV, we have 20 mils of 0.3 molar. What's our concentration? What's our total mils? 40. So we're just splitting it in half. So the molarity is equal to 0.15. And if I have AC minus, I have 20 mils of, 30 mils. No, 20 mils. 20 mils of, 0.35 molar. What's the molarity when I have a total of 40 mils? 0.175. So those are my two concentrations after the dilution. So now what do I do? Yes, and you're going to learn these. The Ka for acetic acid is the same as the Kb for ammonia, 1.8 times 10 to the negative fifth. You're going to get to know that number really well. So pH is equal to the negative log of 1.8 times 10 to the negative fifth plus the log. The ion goes on top. What's the ion's concentration? 0.175 divided by the acid's concentration of 0.15. 4.811 is 12 is our pH. So that's faster than a rice table, yeah? Okay, so I would use this. I think it's easy. It makes buffers easy. And it cuts down a little bit on the solving you have to do in the algebra. Okay, this is a fun one. We'll see if it comes out better this period than last period. They picked a very, very odd acid, made numbers freaky. Specify the reagents and specific concentrations of each reagent needed to prepare a buffer solution which would have a pH of 4.19. So, pH of 4.19 means it's probably acidic, right? We could get acidic with basic stuff, but the numbers would be wacky. So I'd rather pick an acidic system. So, give me an acid that's weak. What would you like? Acetic acid? Okay. We're going to go boring in second period. Acetic acid, and its Ka is 1.8 times 10 to the negative fifth. What else would we need then with acetic acid? We'd need something that had the conjugate base in it, right? Acetate ion doesn't sit in a bottle on the shelf by itself. It's going to come as a salt. So what kind of salt would we probably need to add? What? Sure. That's really expensive, but sure. Cesium acetate. All right. So the question is, what molarity of each of those two things, how much would I need to actually get a buffer of that pH? So I'm kind of going to do a backwards Henderson Hasselbach. And I'm going to just solve for the ratio. Okay, so if I put in 4.19 is equal to the negative log of 1.8 times 10 to the negative fifth plus the log of x, we know what that x is equal to. That x is equal to the acetate concentration over the HAC, which we can solve for in a minute. Right now, just give me what that ratio is. Go ahead and solve. I don't have the answer to this because every period is different because people tell me different weak acids. So. Can I get a second on that? Those are really small. $7.64? Okay, can I get a second? No?
I have 3.5.
That sounds better, yeah. All right, x is equal to 3.58. 3.58 is x. Okay, close enough. So, that is this ratio. So we could do any two combinations of concentrations that would give us that ratio. We could do 3.58 to 1, or we could do, what's half of 3.58? What? 1.79 molar, 2.5 molar. I think this sounds more reasonable for us to make. Okay, so, but again, I'm not going to be picky. So you could put 3.58 molar of the cesium acetate. Well, after you mix them, it needs to be 3.58 molar, and create a 1 molar solution of acetic acid, and that will give you your correct, oh no. Oh no, where did that go? That is not a good thing. Okay. All right, so what would your answer be? I would say we'd need, which one do you want to use, 3.58 or 1.79? 1.79. So we would need 1.79 molar cesium acetate with 0.5 molar. Ah! You guys still here? Testing? Okay, I dropped my microphone on the floor. With 0.5 molar acetic acid. And if you mixed, that would be the final concentration after, that would give you the appropriate pH. So this is actually a lab you're going to be doing. At the end of this unit, I'm going to give you the solutions, and I'm going to say, this is your target pH, have fun. And you have to make it, and I check the pH. It's good times. It's a great lab. No cesium or francium acetate, no. All right. Given a solution of ammonium chloride, what additional reagent or reagents are needed to prepare a buffer from the ammonium chloride solution? So we have ammonium chloride. If we want to make a buffer, what do we need to add to that? NH3. Y'all see why? This would be a conjugate acid to the weak base of ammonia. If it's a salt, the salt's always going to contain the conjugate. The salt will never contain the original acid or base of the system. Okay? So, NH3 is the answer. Now, explain how this buffer resists changes in pH when, so remember, this buffer now contains NH3 and NH4+. How does this buffer resist changes in pH when moderate amount of strong acids are added? Buffers have a buffering capacity. We can add strong acid to a degree, but it's eventually going to run out of one of the two things if we keep invading it with stuff. So moderate amounts of strong acid. What is that going to react with in our buffer system? NH3, and it's going to make NH4+. We turned a strong acid into a weaker acid. That's how it's resisting changes in pH. What about moderate amount of strong base? What is it going to react with? The NH4+ part, and it's going to make a weak base plus water. So we went from a strong base to a weak base, helping to maintain our pH stability. And we got water, yeah. Now let me ask you this one. This is a good question. A portion of the buffer is diluted with equal volume of water. So I take 500 mils of the buffer, and I add 500 mils of water to it. What does that do to the pH? Is it going to send it closer to 7? Is it? Let's think about Henderson Hasselbach. I'm hoping this will lead to an aha moment. When we put in 500 mils of water, remember, these are both milling around in the beaker. If I put in, it was 500 mils, and I put in another 500, what did I do to that concentration? Halved it. What did I do to this concentration? Halved it. What did I do to the ratio? No change. The ratio did not change. Since the ratio doesn't change, the pH doesn't change. Does that make sense? This number stayed the same. What it did do, though, was now cut that buffering capacity in half. Because now, if I were to take some of that buffer and use it to do something, that buffer wouldn't have as many moles of ion and acid per milliliter as it had before. So its capacity would be less, but its actual pH would be the same. Okay, does that make sense? All right, last problem of the day, and it's my favorite. 1983. This is before I took the AP, like really long time ago. I love this. A, I love the font. B, I love the names. Specify the properties of a buffer solution Describe the components and composition of effective buffers. So first off, what's the buffer do? What's its job? Help stabilize pH. So that's what the property is. Stabilize pH. And what components do we need to make a buffer system? Or weak base and conjugate acid. Awesome. Now, the word effective. When you see that, I don't think you'll see it ever again, but what an effective buffer is when this is true. When is that true? When is the pH equal to the pKa? When the concentration of the ion and the acid or the ion and the base are the same. Yeah, at the half titration point. Why is that considered in the world effective? It's effective because it can take equal hits of acid or base, whichever. So it will work in most situations the best. Now, if there's a situation you know you're going to have a lot of acid thrown in, you want a big conjugate base concentration. There's a lot of base thrown in, you want a big acid concentration. But when they use the word effective, they're saying that these are the same, and that goes away. Okay? All right. An employer, you guys are interviewing. And 4 applicants for jobs as lab technicians in your labs. And you asked all your applicants to tell you how they'd make a buffer system, what they would use to make a buffer system of a pH close to 9. So Archie walks in with his red hair and freckles. I think of Archie from Archie Comics. And says he would mix acetic acid and sodium acetate. Is that reasonable? Acetic acid, sodium acetate. Is that a buffer? Yes, that's a buffer. Okay. Well, let's look at all of them. This is after the interview. We got to look at all our applicants. Beulah, unfortunate name, says she would mix NH4Cl and HCl. No. Why is that not a buffer? HCl is what? This is a strong acid, so she's not even in contention. That's not even a buffer. What about Carla? Carla says she would mix ammonium chloride and ammonia. That is a buffer, and it's a weak base and a conjugate acid. Dexter says he'd mix ammonia and NaOH. Dexter's dumb. He mixed 2 bases together, a weak base and a strong base. Oh, Dexter. D is for dumb, not for Dexter. No. And Beulah wasn't much better because hers was a strong acid and a conjugate acid. So that's 2 acids. So yeah, Beulah and Dexter need to hit the road, go work at McDonald's or something. They do not belong in the lab. But question is, who would you hire? I know who I'd hire. One of them is better. Both buffers can hit that pH, but one of them is better. One of them is a lot easier and is going to be something I can actually do in the lab. Carla. Why Carla? Yeah, she has a basic system, right? It's our weak base and our conjugate acid. That would be more inclined to give us a pH close to 9. The numbers would be easier. We could get Archie's, if she takes a job with someone else, I'd call Archie. I mean, we can get to a pH of 9, but the numbers would be kind of skewed because that is an acid system. Huh? The real MVP is Dexter. Dexter just he's pretty basic in many ways. Ooh, yeah. All right, so that's it for today. Work on your homework. Just get used to recognizing and identifying. Looking at the test, majority of you did great. I'm very much happier this time than I was with the last test. Some of y'all stepped it up, I think. Fear of God or something. I don't know what happened. So I'm much happier with those grades. But those of you who are struggling, it's still with the hydrolysis. I had people still not split up into ions, and people trying to add water to the whole salt, or people try to add water to the actual parent, not the ion. So hydrolysis is still pretty weak. We got to get that straightened out, because what we're going to do Monday puts literally all of this stuff together in one problem. Okay, so make sure you have a strong thing. I want you to come and do test corrections quickly. I get really irritated when things happen at the last minute. Like I had a department chair meeting the last day of the day to do test corrections, and I wasn't in here for it. Sorry. And so people were trying to scramble in and getting upset that I wasn't. I'm like, you know, you had 8 other days to do it, and so just get them done quickly. Things happen. People get sick. You know, this is a privilege. This is not something I have to do. So you need to get in here quickly, get them straightened out before we hardcore get into this stuff. Get those errors fixed. All right, that's it.